Hello and a warm welcome. My name is Nick Coe and I'm with Corrosionpedia, the online hub for corrosion professionals. Just a reminder, today's webinar is being recorded and we will send out a link to the recording shortly after the presentation. Don't forget as well that you should get your questions into the Zoom Q&A console as we go, and we'll get to them at the end of the presentation. Moving forward, today we're proud to present Water Pipelines, Prevent Corrosion, Eliminate Leaks, presented by GPT Industries. It is now my pleasure to introduce you to today's presenter, Ian Kinnear. Over to you, Ian.
Thank you very much, Nick, for that warm introduction. And thank you to everyone for joining me on today's webinar. I just want to start off, we know how expensive time is, especially these days. Everyone's strapped for it. And so we just really appreciate you joining us. And I hope that there's something here that can provide some value for you down the line. As Nick said, my name is Ian Kinnear. I'm a sales and applications engineer at GPT Industries, and I'm moving into the product manager role for our flange isolation kits as well. I've been with GPT for coming on about 5 years now, and through this, I've been able to really see and work with all the applications that we're talking about today. So actually have some hands-on, actually be in the field, and I just hope I can pass on some of what I've learned and what I see every day come across the desk kind of in that applications engineering role. And as Nick said, this presentation is targeted at the water market, and specifically to give tips to work with preventing corrosion in water lines, eliminate the potential for leaks when you use your flange isolation kits, and just how to effectively use isolation in these kits in general. This can also be applied to really any flange isolation kit that's being used in industry, but a lot of stuff we're talking about is size-wise and everything directed at the water market. As we know, isolation is commonly used in water applications, right? And it's critical that when a flange isolation kit is used, it performs both its job of isolation and sealing, which is what leads us to the prevention of corrosion in the lines and eliminates any lost products in the form of leaks or whatever it may be. And from our experience, why we're having this specific to the water market is that we do find that in this industry, there are some unique challenges that we don't see in oil and gas or other applications, but they can be mitigated pretty easily if they're just understood, known ahead of time, relayed, and just have a framework of mind around them. So my goal is to share some of these with you today so we can give ourselves kind of the best chance at that optimal performance. And with that being said, I have a little poll just to start off, just to get some engagement right now. And so you'll see, you should see a poll be able to come up on your screen, and it's just looking at some of the sizes, the large diameter sizes in our flange isolation kits. And we'll just give a couple seconds to just be able to answer that. And it just gives me a little bit of a framework on what I can look for in terms of sizes that are coming up and kind of what you guys are seeing in the industry and having to deal with, because a lot of the topics, this first topic is going to be a lot in large diameter pipes. So just an understanding if that's what indeed a lot of people are working with. All right. Thank you very much for that. Make sure my screen is sharing again. Wonderful. And with that, I'll jump right into it and kind of talk about the two major topics, and one you can already guess from that poll that we see when we're dealing with water applications. And the first one that I'm going to be kind of diving into is to give a better understanding of the issues and challenges that can occur with that large diameter pipeline, where isolation or really sealing needs are at a high concern, and how we can solve them. And large isolation gaskets play an important role in pipeline protection. And the reason that it has such a focus is because how extremely costly failure is, right? With these large sizes, there's a lot of installation costs. If you have to deinstall and reinstall, the gaskets themselves cost, the time, the labor, the effort. There's a lot of cost in this regard. And so getting it right the first time is very important. Um, I'm just seeing the results to that poll. So we have a good mix. Yeah, thank you. And we really believe that with some of the knowledge here today, we can reduce a lot of these costs dramatically and make these installations a lot more seamless, make it so you only have to do it once. And with that being said, our experience has led us to understand quite a few challenges with the large diameter isolation gaskets, and just want to bring visibility to this. And you're going to hear me say throughout this, you're going to have my contact information, and no matter what it is, let me help you, let us help you. We've been through these challenges, we've seen them a lot of times, and if we do it up front, it's always better than doing it on the other side. And the next topic I'm going to be talking about is still regarding water, but it's more of the impact of water absorption and permeation on standard gaskets and then isolation gaskets alike. And so it's not uncommon at all to use standard gaskets in applications that require isolation. But there are some issues with this, and I just want to kind of give a further understanding to this and an understanding of why isolation gaskets are used in these applications instead of just standard sheet gasket or spiral wounds or whatever it may be. And understanding both of these and allowing us to kind of help and give a framework of that can really help with just getting it right the first time and having a successful kit that does all the intentions that we're actually looking for. So as a manufacturer, we're fortunate enough that we see a lot of the conditions around the world. We get to see how these impact our customers and how they're changing throughout time. And as we all probably know, pipeline conditions are always changing. This results in challenges that we haven't seen before and we have to face. And a lot of these challenges relate to both of the topics that I'm going to be touching on today. We've seen a really a big growth in large diameter lines in general, again, which is why I asked that poll question. And we continue to expect to see these large diameters as more water needs to be moved. We're seeing them built all throughout the country, all throughout the world. And with this, we've seen significantly more segmented type gaskets, which I'll get into more later, but that's when the gasket OD meets a certain diameter. Sometimes the gasket has to be joined for multiple sheets in these larger diameters. And we've been producing these for a long time, but they provide challenges. And it's something that we see, and it is a pipeline change that we see issues with as they go. And there's a lot of different types of flange configurations. And of course, this brings with different design requirements for it, and the penalties for not meeting deadlines on these requirements can carry significant costs. So delivering, installing, successfully hydro testing on time, all very important. And then, so it's a lot of that increased demand to meet a timeline. And with this, we have less skilled installation resources. Kind of by the day, we're seeing reduced staff become a norm, or not being able to staff to where you want, I think is where everyone finds challenges these days. I know we certainly do. And so I think it's just becoming something that we're having to deal with is less people, less skilled installation. And so getting it right the first time, understanding these challenges right up front on these water lines is just really important and can have a huge advantage in saving costs in that regard. And so my first, I'm going to go over kind of just a high overview of both those topics, and then I'm going to dive into the large diameter one first. And I first just wanted to give a quick highlight of the main challenges that cause the most frequent issues that are seen with large diameter pipe. There are more than these, of course, but kind of from that apps engineering desk, these are the ones that I see come across most often. And I wanted to just give a highlight to in our time we have today. And first and foremost, the most common issue that I see is regarding sealing. So not isolating so much, but getting a proper seal on these large diameter flanges. If anyone's had trouble with isolation gaskets in the past, it's not uncommon, and a lot of times on these larger diameters, it becomes more and more of a challenge. And we all know the story. Some of these take days of installing one gasket. You have 60 bolts, 62-inch bolts, really high torque. We finish, hydro test, and it leaks. And I think nobody rips their hair out more than when something like this happens, because now you have to uninstall, replace the gasket. You might have to wait a time for that gasket to be made, reinstall again. Definitely, this can't be an acceptable norm. This can't be something that happens, and we do see it happen quite a bit. And so we're going to discuss why this happens frequently. And as you can see there, many times it's due to where the ID of the gasket and kind of most importantly, where the seals are landing on that flange assembly. Concrete lining influence this, inconsistent pipe diameters have an impact on this, valve IDs have an effect on this. So it's just something we're going to talk about and be aware of. The common issue with these is the gasket design that I just talked about before. At a certain size, the gasket must be segmented. It must be brought together. It can't be made out of one sheet of material. And we've seen a lot of troubles with this. It takes a little bit of expertise to have the results in this that you want with the gasket. And the same goes for the seal and the groove design. With these large sizes, the margin for error becomes a lot smaller. The loads are higher. You have a lot more area around the flange where a leak just can't occur, right? Instead of a 2-inch flange, there's just not many area where a leak can happen. A 60-inch flange there is. So getting perfect compression is a lot more of a challenge, and the quality of design here really does make a difference. Next, we'll move on to more of isolation concerns. So those were more actually getting a proper seal. We also need to get isolation, and this occurs in these large diameters with sleeve length and sleeve quantities. Many times we're working with AWWA flanges, and the only thing that typically changes between these pressure classes is the flange thickness. We need to know the flange thickness to get the sleeve length correct and properly isolate from one flange to the other. This is the same if a valve is being used, right? So a valve could have a different thickness than the typical flange assembly, or it could be sandwiched in, and we need to know all of this to get the sleeve length correct. Does the valve have tapped holes? That's something that we need to think about and account for. Is there inherent layback in the flange? And then lastly, an issue that I see more frequently than you would think, and I really just wanted to put it out there just to get some education, just to talk to you guys about it, is the type of bolts that are used in these cases. The last thing we want is for 60 of these 2-inch bolts or whatever it may be to be purchased on site to discover the sleeves don't fit. It's something we can avoid from the start, and it's a very expensive mistake when it does happen. So just want to bring some awareness to it. And before moving on, I also want to mention, kind of just to give you a perspective of what's coming, some big questions around water absorption and permeation that I'm getting to get to later, and kind of understand the impact that these have. To start, I've mentioned both absorption and permeation. I just want to first give clarity on the difference of those, and see what materials will be acceptable to be used kind of as a result of both of them. They are different, and different materials act differently for both of them. So next we'll really look at the impact that both have on isolation and on the gasket performing up to the levels of what we bought it for, right? Isolation gaskets do cost more, but they do provide a purpose, and we need that purpose when we do have these situations. So in line with this, it's kind of giving that criticality to a true isolation gasket and not using a sheet gasket, and some of the reasons why in conjunction with the sleeves and washers. I'm also going to talk about hydro testing isolation gaskets. Not doing this is kind of a common practice, and it's a direct result of these. And this is another headache isolation gaskets can provide. And there's some solutions, and I kind of want to talk through it. And I know I'm going to open up the door, and people are going to come ask me questions after on hydro testing, and I'm very open to that because it's an interesting subject that I can kind of go back and forth on. And so, with that being said, lastly, just want to touch on what to be aware of, how we can avoid these issues that we're talking about, and put the best solutions out so that you are getting the performance you're expecting. You're not seeing corrosion, you're not seeing leaks as a result of corrosion, and so on. So going back to the first challenge, so we're going to go with large diameter pipe first. And that first challenge that I brought up is, where does the ID of the gasket and where do the seals land on the flange face? So of course, to create a proper seal, it's necessary that the sealing elements of the gasket land on a proper sealing surface on both sides, right? These isolation gaskets have usually small seals. They're a strip that goes all the way around, and that seal has to land on a proper sealing surface, right? This means that whatever configuration we have, whether it be a pipe mating to a valve, a pipe mating to a pipe, or a flange mating to a valve, flange to flange, a concrete line pipe to a valve, whatever it is, we need to ensure our seals land on a proper sealing surface on both of these in the configuration. I'm going to show some figures next of what it might look like to have concrete line pipe and the effects of this where our seals might not be landing on a surface that we want. As I've talked about, concrete lining is extremely common on these large diameter water pipes. So sometimes that concrete lining goes all the way through the flanges. Sometimes it stops right at the flange. As you can see in the picture here, there's also a transition between the concrete lining and the actual flange. And if our seal lands right in that crack between where those surfaces change right there, we're not going to get the proper compression that we're looking for. So it's just something that knowing it up front and understanding that our seals need to land on a proper sealing surface. That's no matter what gasket goes in, you need it to land, you need its sealing elements to land on the sealing surface, right? This will, as long as we know this and there's awareness to this, we can go ahead and make a difference in this regard. And so for this to be done, we're always looking for the flange ID and not the pipe ID in these cases, where there's concrete line pipe or these large diameter cases that we're looking at. So this is a model of that I made up, and there's only one side of, we're only seeing one side of the pipe right here. And if you can see my cursor, this is the gasket, here's the gasket seals, here's the gasket ID. In this case, and I took this directly from an application that I had, the valve ID that this is mating up to is right here. And this is the value that we got to make our gasket ID. So here you can see a concrete lining come up and then our flange face here. Our sealing elements are only partially landing on a sealing surface just because we made the flange ID to what was told. And this concrete lining doesn't come all the way through. So we're not getting compression on the seals that we're looking for in this case. This will often result in a leak. You're also going to have, now the flange is sitting in the flow, or the gasket sitting in the flow of the pipe. You're going to get fluttering on that gasket, lifting these seals off as the pressure comes through. So with only a small part of that seal making contact, it really makes it difficult for engagement. And this is something we see quite often. We might even get just only the pipe ID in this case, and still our seals might not land where we want. We want them to land on the sealing surface itself, not on the concrete lining that might not even be existent, not down here, but on the flange. So we need to know the flange mating types and drawings of these flanges as well. If we would have known in this case what was on this side, which I'll show in my next slide, it would have made all the difference. But this is kind of what we're looking at, is when these mate, we need to know the ID of both sides so that we can just ensure that the seals land. And that's no matter what gasket it is, whoever manufacturer you're working with, just ensure that your seals are landing. This is probably not going to pass a hydro test, and you're going to get a leak that we talked about right from the start. So here's a case that was done properly, and I'm making sure everyone here is awake because I flipped the sides of what we were looking at before. Why I did that, I don't know, and I apologize for that confusion. But in this case, we have a concrete lining on this side, and we have that valve we were talking about on this side. So before, we were matching this valve ID. So we were landing concrete lining, our seals were here. Now we're matching this flange ID with the ID of our gasket right here. So our seals are much further up. They're landing on the flange face and on the valve face. We're getting a great seal in this case. We're getting our seals compressed. We're landing on both flange faces. And we don't have any concerns. In this case, we don't have the gasket ID in the flow, so it's not going to flutter. We're getting compression on both. This is what we're looking for in regards to being able to get a proper seal. Any manufacturer will be able to make their design so that it's this. And this is what I can always help you with. If you reach out to me and don't know what to look for, just dump it on me and we'll be able to figure it out. We'll be able to get there. But in this case, what it took was knowing what the flange ID was and what the slip-on flange, what the valve ID was, and what the slip-on flange ID was as well. Knowing there's a concrete liner, we just want to bump it up. So it's something I know this seems specific, but this is something I do see, I mean, truly on a weekly basis. These coming in, and it's not, I know information's hard to get. We're going end user, contractor, distributor, us, and it's hard to get all the way down that channel, but it really does make all the difference. And I just wanted to highlight this and just bring it to light. So again, all we needed, we just need the fabricated steel drawings from the pipe manufacturers. That final flange ID is really what we're looking for to be able to create what we need, to be able to get that proper seal. And this is the number one kind of sealing failure we see with these large diameter pipes. We see it at other times in any type of pipe, but with the concrete linings, it's something that comes up much more with large diameter sizes. The next major challenge that we see with large diameter pipes, as I mentioned, is due to gasket design. As I talked about, that margin for error gets just increasingly smaller, and the quality, the engineering, how the actual gasket's made makes a huge difference. And it's just something to be aware of. Large gaskets require what's called segmentation. So I said this a few times, but that just means that pieces must be joined together on the manufacturing side. If the gasket material comes in sheets, and if the OD of the gasket is bigger than that sheet, then it has to be cut out of 2 sheets and brought together to make one solid circle. And so I can give you exactly what the ODs would be, but really, yeah, it's just when you can't cut a circle from one sheet anymore, you have to cut it from multiple and segment them together. And it is kind of a science, and the design of this is really important. You can see here that this isn't a good design for segmenting. A leak on these occurred right at that joint because that surface is uneven. The joint's not at a proper length, and you can see it's actually cutting right through the steel. So there's just a leak path right at that segmentation. So we can imagine that there's almost no way for this to be able to seal. There's no chance for that gasket to even make a seal. That leak's going to just cut right through the seal. And it's something that we do see quite often. And it's just, I just wanted to highlight it. That splice, that segment does make a big difference. And I can kind of show you a different design. And this is one of ours, but just there's many different designs that can work in this regard. And I know we at GPT take a lot of pride with it. We take a lot of time with it. And we've been manufacturing these for a long time. So just to show it's just, before you install a gasket, make sure that segment, the seal is going on top of that segment. That segment isn't going through that seal itself. And the ideal transition, the ideal right where that's happening, it should be kind of, you can't even feel it. If you close your eyes and run over where that splice is, there should be no thickness change. There should be no change in feel. You can't really even tell where that segment happens if you have your eyes closed, run your hand over. That's when you know you have kind of that ideal gasket design in these large diameters, and it's just something to be aware of. The seal should then run over top so that we're not actually seeing the transition in the sealing realm. There's no direct leak path through. And this really does make a huge difference in these, and it is a concern of a lot of end users, a lot of distributors, a lot of contractors in these large sizes is having to segment together. But it's something I know we take a lot of pride in and have a lot of success with. So we just wanted to kind of share what that looks like. Again, sticking with the larger the pipe and the larger the gasket get, that margin for error. There's a lot of ways something can go wrong. There are the most points where a leak can occur. There's more stresses. There's more difficulties to install. So a gasket has to be very specifically designed to be able to get compression in this regard, to be able to properly compress against and make sure we're actually getting a seal. In that picture to the left, you can see the difference in sealing elements. This was a large diameter gasket taken out. And in that red gasket case, there was too much rubber for the groove. So when there's too much rubber for the groove, this is going to lead to a leak down the line. It might not right away, but it's going to as that material starts to flow out of the groove. So you want to make sure that that seal has somewhere to compress into within the groove itself. So it's called a volume void ratio. So when that seal gets compressed, it has somewhere to flow into. In this case, there was nowhere for that seal to flow into, so it flows along the edge, creates a leak. In smaller sizes, I would still think a design like this is going to have a leak, but in larger sizes, there's just no way you're going to get the compression all the way around that you need. On the right side there's not enough rubber in that groove. So this was kind of a cheap design where there's not enough rubber in the groove, and you can tell there's just no way that's going to actually have a seal to be able to be made. And so it's just something to be aware of. Just that seal design is really important in these sizes. The next thing that we talk about is the sleeve length not being correct. So as you can see here, the sleeve, and what the sleeve does is isolate the the bolt from the flange. So you can't get any current passing from the bolt to the flange itself. You're isolating there. And to get the sleeve length correct, we need to know the thickness of everything the sleeve is passing through. So as I mentioned, on AWWA flanges, the tables and classes that the flanges refer to typically change only that flange thickness. And you can see that in turn affects the sleeve length of what we're going to be passing through. So it's very common for when it comes in, this table or class is not provided to us. We have to take a best guess of what we're actually looking for, of what you actually have, what your actual thickness of the flanges are. And this can lead to sleeve length errors if not caught. And so also if a valve, so say you're mating up to a valve, that might not have the same thickness as a standard flange. So if we don't know there's a valve and we're assuming it's a standard flange, we're going to have a sleeve length that's a little bit off. So just understanding this is really critical. And I'll show you, here's a case where a valve is actually sandwiched between two flanges, which is a configuration that we see quite a lot in these large diameters. So you have a flange, a valve sandwich, and then a flange. In this case, if we know, so here the sleeve length is shown right, and it's because we knew that there was a valve and we knew that there was an additional gasket on the other side, so we can account our sleeve length for this and make them longer. But if we don't know that there's a valve in place, if we don't know there's an additional gasket, then we don't know to make the sleeve length longer, right? And any manufacturer is going to face that challenge. You're not going to know that sleeve length has to extend all the way through. So really all we need to know in this case is that there's an additional valve. We need to know its thickness. There's an additional gasket on the other side of the valve. We need to know its thickness. Unless one of our gaskets being used, then we of course already know its thickness. And here, so it's just having that information and that understanding that we need that sleeve length to be able to make it. There's nothing worse than, well, I said there's nothing worse than hydro testing getting a leak. Maybe there's nothing worse than installing one of these and doing an isolation check and finding out that your dang sleeves are just a little too short, right? And now you have to order new sleeves and get the new sleeves in. Can be very frustrating. So it's just to get it up front and make sure we have the right sleeve length. We're going to install it. We're going to pass isolation and be able to move on and not have to do anything. Another case that comes in on valves, on these large diameter valves, almost always there's going to be a certain number of threaded holes on the valve. With a threaded hole, our sleeves can't pass through these, right? A sleeve can't pass through a hole that's threaded, a bolt that's threading into the hole. So for these cases, just provide this information. We can still provide isolation. It's just we're gonna want to stop right before that threading starts. So maybe we can go through the flange with a sleeve and then stop it right there. And that's something that we can always help with. We can always take it into consideration. We'll get the right quantity of sleeves that work through the holes and the right quantity of sleeves that work on the threaded holes, and you'll be able to isolate all the way through and you're not going to run into trouble. So it's just something to be aware of. Threaded holes on valves. We have solutions for it, it's no problem. Just need to know that and understand it going into it. And this I brought up, and can be especially painful and expensive for these large diameters, is the correct use of bolts and studs. So the highest recommendation that we have to use is studs with 2 nuts on each side. So 2 hex head nuts like we see there on the left. The reason for this is because we can ensure that the sleeve is going to fit over this stud and that the studs provide the ability to obtain more accurate torque values for a gasket than bolts, because studs don't twist during tightening. So if bolts are being used, though, it's incredibly important that these don't have a shoulder on them, like on the bottom. Shoulder bolts are very common, especially in these larger bolt sizes. We see it quite often. And the issue is you can see here that these shoulders have a large kind of uncontrolled diameter than the threaded section. So our sleeve can no longer pass over this. So you're going to try to install and the sleeve isn't even going to be able to go over these shoulder bolts. So then you can't use the sleeves. The entire kit becomes compromised. Now you just bought an isolation kit that can't isolate, or you bought a bunch of bolts that can't be used with the kit. Either way, it's just an expensive thing. Just know up front. We want these bolts to be threaded all the way through, and use studs whenever possible. Studs are the best, the highest recommendation that we have. So these are the biggest ones that I have on large diameter pipe. And now I'm going to move on to some of those water absorptions. I'm just going to start with another pull. It's going to be a really simple one. And we're going to be able to jump through it really quick. But those were the biggest ones on large diameter. And please just ask me any questions that you have on that. We'll get to them after, or I'll have my contact information on those large diameter. It's just, we know how costly those projects are. And I just wanted to highlight just a few of the big things that we see that give flange kits a black eye in those large diameters, and also just cause the most trouble that we see. And this is a simple yes or no poll, and just trying to see if, I know it's very common for non-isolating gaskets to be used in applications that require isolation. You put in one of these gaskets and then pair it with sleeves and washers. So just trying to get, just trying to get an honest gauge on what that looks like. And with that, I can continue to talk if anyone votes in, and then we can move on. So again, this relates to water because it's the impact of water absorption. Okay, so seeing the results, 76% no, 24% yes. So yeah, thank you guys very much for that. And we'll talk a little bit about it and why that's the case, and what we look for in these applications. So I've already gone over these general questions, so I'm not going to ask them again. But it is really important to understand the impact that both of these, that water absorption can have on the material that is being used to isolate. And the impacts that water, or really any media that permeates, can have on an isolating material. These both have a huge impact on how the gaskets can perform, how we intend for them to perform. And we really want to educate on why this is occurring, what you need to be aware of, and some solutions just to look for in this regard. And so I apologize, this slide has a lot of text on it. But there is a difference between water absorption and water permeation that I wanted to just touch on here. When we talk about absorption, I usually think of a sponge. This is the amount of water that the material will bring in and hold when in contact with moisture. And what makes this key is that it occurs in a natural way. So the water's not being forced into the material, but it's actually the material's just soaking up it kind of naturally. Just like a sponge will do. It just soaks up that water. It's not being, there's no pressure that's pushing it in. So different materials will absorb water at different rates, right? A sponge does different than a piece of wood, or whatever it may be. And as you can likely see where this is going, the electrical properties of a material can be greatly affected by the amount of water that it's been absorbed, right? That's been absorbed. We'll touch on this here on the next slide. Permeation, on the other hand, is the amount of media, for simplicity's sake, we'll use water in this case, but really any media that will actually penetrate through a material by force when it's in contact. So permeation occurs, sorry, I just want to make sure my screen was sharing, as a result of a pressure gradient, right? So it occurs under pressure and not naturally. So the higher the pressure, the more permeation that will occur. And this is dependent on what material you're actually pushing through, what media is actually going through that material. the pressure, temperature, among other things. So small molecule gases are going to permeate a lot easier than liquids. This is one reason why sealing hydrogen, as just a side tangent, can be much more difficult than sealing water, for example, because that hydrogen can actually go through the media itself. Higher pressures are going to force more permeation than lower pressures. More porous material allows more permeation than denser material, so on. And it results in some of the similar things as absorption, but in a different manner, in a way. So the question, why the heck does all this matter, right? And the bottom line is that we don't want water, we don't want moisture, we don't want media, whatever it may be, inside of our gasket material. In the case of water being absorbed into the material, water for our purposes is considered a conductor. Electrical current can pass through water, which is exactly contradictory to what we need our isolation gaskets to be doing. So electricity is going to take that path of least resistance. And if water's present, boom, we just got a new path that it can take, where the isolation gasket was trying to block that current, that electrical current. So when water is present in a material, the electrical isolation properties of that material, whatever it may be, are going to be significantly lower. So a material that may isolate when dry might not isolate when it actually comes in contact with moisture, when it actually comes in contact with media. So that's what we're kind of thinking about, and that's what I'll get into in the next slide. And we also need to get just be aware of any type of media permeating into the gasket material, as this can have longer lasting effects in terms of chemical compatibility, material performance, overall leak rates. The more we can avoid media permeating into and through the gasket, the more assured that we can be that a proper seal is being made. The material would be able to perform through the life of a system. So knowing that, first on the water absorption, knowing that as a material absorbs more water and more moisture, its dielectric properties are going to be affected. We can now understand why, even if some materials have a high dielectric value when they're dry, they can't be used as isolation products, right? Once they're put in service, there's going to be moisture present. And as soon as this material in service begins absorbing the water, its dielectric value is going to drop dramatically. We're not going to be able to isolate any longer, right as we're putting fluid through this pipe. So this is one of the reasons why sheet gasket material, CNAF material, rubber material, and others aren't recommended for isolation, because right as they go in service, they no longer isolate. So you might put them in, install them, they're isolating because they have dielectric values. You put your CP current on, and right as you start running that water through the line, your CP, you're no longer blocking the CP current. So you're no longer getting the purpose of why you were isolating in the first place. And this can be dangerous. This can be costly, and you're going to get other types of things in that regard. So you can see here, GRE, that G10 and G11 is one of the oldest standard isolating material. We use it in many of our gaskets, and you can see why. It has a really low water absorption rate, 0.1%, 0.09%, very low. Phenolics, an old isolating material, has a little bit of a higher water absorption rate. Sheet gaskets absorb much higher rates of water, and over time, they're going to lose their dielectric properties if they have them to start as a result. There's also some other reasons that these types of gaskets shouldn't be used, but they're not super relevant to this, so I'm not going to get into them. But if you're interested, reach out to me and I'll talk to you about them. But water absorption is one of the main reasons that we do want to actually make sure we have a proper isolation gasket in place. So we saw GRE as a great material in terms of water absorption. And now we're going to look into permeation. Permeation is when the media is driven into the gasket material under pressure. And something that we've been trying to relay, to educate on for a long time, is that GRE, great in water absorption, it is a permeable material though. And this is actually why metal cord isolation gaskets were invented. After it was understood that isolation was necessary to break up dissimilar metals or make CP effective, the issue became that as pressures continued to rise, leaks were occurring. And these leaks weren't going between the gasket and the flange, so our seals were working, but they were actually going directly through the gasket itself as pressure was going up. via permeation. So this is especially found with gas being the media, but we've actually seen it with liquids as well. We've seen it with water, we've seen it with oil. And so it's worth bringing up with permeation. So GRE laminated on a steel core was introduced as a solution to this, as steel is impermeable. So we no longer saw these leaks going all the way through the gasket. There's still permeation into the GRE itself, but it's no longer a leak. This is actually why metal core gaskets were invented. And it's kind of not hard to make the leap that if media such as water permeates into the GRE at high enough pressures, this might have an effect and impact on electrical isolation, kind of like absorption. So it's just something to be aware of. And in addition, many times at these high pressures, we're dealing with other medias than water. So if you have other medias that could be a little nasty, H2S, CO2, whatever it is, this is a little off branch to the water topic. And they're being driven into the GRE, we could actually start breaking bonds and having some chemical compatibility issues. So it's just something to be aware of. And as you see, there's been step changes in technology that GPT has done and the industry has done over the years, really with permeation in mind, to decrease the permeation that these gaskets see. So we put in a steel core, put in an ID seal so that the media actually never comes in contact with the permeable material. And finally came up with a gasket that doesn't have any permeable material in it at all, which is kind of the best case scenario to do. And here's a picture of why this happens with GRE. It's made with millions of microscopic kind of glass straws in an epoxy matrix. And in both conditions, we've seen that gas and media can actually permeate. They can force their way right through these cracks right here. Material does matter. So higher grade GRE permeates significantly less than lower grade GRE. So we work really hard on getting that highest grade of GRE, and it does make a huge difference. The quality of its materials make for much better results in being able to see this permeation. With that being said, it's still not perfect. The design of the material just allows for permeation to occur. And it's just something to be aware of. And it's why there are pressure ratings on the linebacker or the homogeneous GRE material without a metal core, is that you don't get that leak from permeation directly through. So when we hydro test an isolation gasket, the idea of permeation can be at the forefront of mind. So a lot of times operators don't hydro test with isolation gaskets. They put a dummy gasket in, hydro test, take it out, and then put the isolation gasket in. This, of course, is costly. It takes time, and you're not really testing the system. We see this permeation because hydro tests go at 1.5 times the operating pressure. So higher pressures, we're seeing this phenomenon occur, and dielectric values can lower. With this being said, and why I said we can talk about it more, water, so these can be used, isolation gases can be used in water applications with high pressure. The concern is just if you take a resistance reading before the hydro test and after, those might be different as a result of water being between the gasket and the flange, or in the grooves, or wherever it may be. You might just lower your dielectric readings a little bit. So it's just something to be aware of. This should not have an effect on isolating a CP system or similar, but there are solutions that you can put in a gasket and have no change in dielectric properties. When you use an ID seal or use a gasket, isolation gasket, with no permeable material, you can hydro test and you're not going to change these dielectric values in any way. So it kind of gives the most confidence to be able to put the isolation gasket in, hydro test with it, keep it in, have actual measurements of the system that you're hydro testing, and not lower the values. So it's just something to think about. It's something to be aware of. I'm happy to talk more about hydro testing, but it is something we see in the water market quite a bit, is a temporary gasket, a hydro test, and taken out. And we do have solutions to be able to not have to do this, gasket solutions to not have to do this. So kind of just what to be aware of here, major takeaways. For electrical isolation, water absorption of the material is key. It's very important to make sure that the material being used does not absorb water. Even if it has dielectric properties to start, it might not once it gets wet. GRE in most isolating material is permeable. Not all GRE is created equally. Lower the quality, the higher the permeability, but all GRE is permeable. That's why there are now solutions where GRE is eliminated from the isolation material, kind of as a result of this. Homogeneous GRE, so with no metal core, just the GRE material that's used in the water market a lot, has a pressure rating because of this permeability. At high enough pressures, we're going to be able to push that material right through as a leak. 600 pounds, typically my tipping point on where I transition. Below a 600 pound, I'm great using homogeneous GRE. Above, I would like to have a steel core. 600 is a judgment call. We can go either way depending on what we're looking at, what temperatures, pressures, media, but that's typically my tipping point as a result of this, because we do see it right around those pressures. And then lastly, hydro testing can introduce water into the gasket material, can change isolation readings. There are some solutions to this. We can talk about that, and it's just something to be aware of. So kind of the takeaways from these. That first one, be sure to use a true isolation gasket when trying to isolate flanges. Where flange isolation is needed, where you have cathodic protection especially, we need that gasket to have dielectric properties to be able to actually block that CP system. To be able to use that CP effectively, we need to be able to block it. Work with, make sure you're getting the highest quality of GRE, taking pride in those materials that are being supplied, or use a gasket that doesn't utilize GRE anymore. But just be aware of it. Be aware that GRE is permeable, and it is a material that can cause leaks in this regard. Utilize metal cord gaskets at higher pressures in critical applications for the pressure ratings. And then hydro testing, you can utilize a gasket that does not experience permeation, or talk to us about it, and we'll talk about readings and see what we can do with the isolation gasket in the hydro testing itself. And with that being said, let's see, 13 or so minutes to answer questions, and I can stay on as long as anyone wants, but just really want to thank everyone for taking the time out of everyone's schedules are busy these days, and I just really appreciate you spending the time with Corrosionpedia and GPT. And I hope it's been beneficial. I hope there's at least something that you can take away, that we can help save costs, save materials, save time. We're always here to help. So my contact information is here. Please reach out any way I can. And with that, I'll stay on as long as I need for questions, but I'll pass it back to Nick to be able to do so.
Wonderful. Thank you, Ian, and couldn't agree with you more. Really appreciate everyone's time today. And of course, some of the great questions that have come through. So thank you as well too, Ian, for sharing your experiences with us, your expertise. Have had some comments that the audience has really enjoyed the presentation and all that you've shared. So again, I know I've sent a couple of reminders in the chat, but just one reminder that you're welcome to get your questions in through the Q&A console at the bottom of your Zoom screen, and we will do our best to get to them. So with that said, why don't we get to some of these questions? And the first that I'd like to share, let me just get this set up, bear with me. And this is there's a bit of a background here, Ian. So I'll go through what this person has shared and then get to the question. Okay. So this person has asked or has said that we've had flange isolations which pass our initial isolation testing after final torque. Upon filling the main, we either have failed isolations or partial failed isolations. I suspect ICT, internal current transfer, for some of these issues. The question is, does a mortar lining have the dielectric strength to prevent ICT? Do you have any other theories for these isolation issues outside of improper installation? Yeah, and that's a great question. It's something that we've seen more and more frequently, is this internal current transfer, and it's usually due to that media being conductive. So you're losing isolation right through that media.
we've had a lot of success recently using our evolution gasket. And the reason being is that it has an ID seal that actually you can protrude that ID seal. So the first thing is making sure your isolation gasket, the ID matches the pipe bore so that there's not a gap between the pipe, between the flanges where media can build up and this current transfer can happen. This is difficult with that mortar line pipe. I don't know the answer to if that lining has, I can do some research into that, if that lining does provide any dielectric strength, but I don't know if it does. So we first want to make sure that our ID is matching the pipe bore in this case, or the flanges, so we don't have a gap between. The next is using an ID seal has a big advantage in this regard because it blocks off any, if you have a metal core, it's easy for that current to jump onto the metal core and then off. And this provides a little bit more, a longer effective isolating distance. So you're isolating at a larger distance. The next is that material has kind of a no stick. So any of the media doesn't stick to it. And so you don't get as much transfer there. And the next is that you can kind of protrude the ID of the gasket slightly in. And we can make sure, I know I talked about today, making sure we didn't do that, but we'll make sure our seals land on the flange face and we have that slight protrusion in these cases. That makes a buildup for the current that has to travel. And these have actually had a lot of success in this regard. And I'll reach out after and talk some more about this, this idea with you and share some things on this. But it is something that we see more and more, and it is a challenge in that regard, where the media is actually conductive enough that it's passing the current through the pipes. Your isolation kit is working as it's intended, but the media is passing that. It's something that we are aware of, and I can share some more with you, but those are some of the solutions that we've worked with. And the first one, I think, first step is making sure the ID matches. And a monolithic isolation joint is also a very good option for this because of that effective isolating distance. If that's capable of your system, monolithic isolation joints can have a big impact in this regard as well. So I can follow up further with some further documents on that for you.
Excellent. And a reminder too to everyone, Ian has been kind enough to share his contact info here on the screen. So, I mean, jot down, I mean, we'll send out a copy of the webinar after, but you're welcome to reach him through his email right there. Let's get to the next question, Ian. So it is, are there any lectures for chemical and steam lines? I work at a pulp mill where we deal with caustic, sulfur, and lots of steam lines.
It's a great question. The reason it's a great question is because that GRE material that I was discussing all throughout this, a big no-no of that GRE material is steam. Steam's a material that has high chemical compatibility issues with GRE. So most isolation gaskets should not be used in steam lines. That steam has enough energy that it breaks apart those epoxy bonds and you actually just get left with glass. And I can show you plenty of pictures that we have after the GRE in steam lines. So we do have gaskets suitable for steam as a result of this. But it takes removing that GRE material. So there are isolation solutions for exactly what you're looking for. Just be very careful because that GRE is not compatible. You will lose bolt load over time and have a failure if you use GRE in steam. So something to be aware of. Our evolution gasket is rated for steam. It's used in steam applications pretty frequently. And it's definitely what I would recommend in this regard. So there are solutions, but it's something to just be aware of for your application.
All right, next, can you recommend any methods for shortening a sleeve to suit conditions in the field if there is a discrepancy?
Yeah, and I work with plenty of customers that do alter the sleeves in the field. Using like a fine tooth saw or some kind of blade and cutting them is acceptable. You can definitely do it. Just be aware the sleeves can split. That material can split pretty easy and it can be sharp. So just as a safety side, just be aware of it. That's why you want to use like a fine tooth or some kind of rotating blade to be able to actually cut the sleeves. And it is something. we can cut to any size that you want, so we can certainly do that, but I understand there are times where they do need to be altered, and so using something of that nature can have success. Just be careful with it, because you can split the sleeves, and you can get kind of fragments, and so they don't work as properly. But you can use something like that in the field to be able to alter a sleeve.
All right, the next question is, what other reasons besides water absorption and dielectric factor are taken into consideration to rule out materials for FIG case?
Yeah. And so I could probably go on with this for a while, so I can follow up with you after, kind of directly. But one of the big ones is that isolation gaskets don't compress at all, so they don't have any creep and relaxation. And this is important in a few different regards, because one, this requires a lot less torque and a lot less stress in your flange assemblies. So less stress means your materials last longer, and they're not going to corrode away from stress corrosion. So just in that simple fact, you'll see isolation gaskets have lower torque values as a result. What also happens is when we're creeping and changing thickness, it's very hard for those sleeves to be measured properly. So it's something just to be aware of, where your sleeve length might not be able to be accurate when you're having that compression and that change in thickness. So that's a big reason, something that we see, of why not to use gaskets such as that. There are a couple others. I can reach out personally, but that's the one kind of at the top of my mind of why, other than water absorption, why we don't want to use something like a sheet gasket or something in isolating applications. It's just those sleeves and washers.
All right, the next question, again, there's a little bit of some context that I'll first share, then we'll get to the question. So we encounter flanges which can have uneven surfaces, either from old installation methods or pitting corrosion. Can GPT start making isolation gaskets which allow for a larger sealing ring to allow for seals when dealing with these uneven surfaces? Usually these circumstances do not have the time allowance for resurfacing flange faces, and due to time constraints, conventional rubber gaskets are used to prevent a leak and get roadways back in operation.
Sure. Yeah, it's a great point. So we do have a gasket model where the seal covers the entire face of the gasket. And this is what we recommend for applications such as this. It's called our RC gasket. So it uses bunanitrile over that G10 material all over the face. So it actually seals all along the face of the gasket. And that would be what I would recommend for these. So we do have a gasket model. That seal design, we do take quite a bit. So we take a lot, there's a lot of engineering that goes into that seal design. To talk about that volume void ratio that I talked about. So that groove is kind of machined perfectly so that when the seal sits in it and compresses, it fills up that groove. And what we're able to do on why they're so thin at times is because you can get a lot more stress on that seal itself by having a smaller area of seal. So a lot of times people think a bigger seal means more sealing, and that's not quite the case, because when you put a force on it over that larger area, you're going to get a lot smaller of a stress on that seal to be able to actually create a seal. So having it thin does have advantages. We can look into some other designs, and we can look into some designs for you of putting multiple seals on the gasket or moving the seals around. I can work with you on that. I'm happy to move the seal to a place where we're going to land on a flange face or on a solid seating surface. Put maybe a couple seals on the gasket depending on the size. Offset the seals. We can do options such as that. Or our RC gasket is something to look into, kind of as that full sealing face. So the whole face of the gasket seals and it is isolating. And that's what we would use a lot of times in flanges such as that. So it's something, we do have a solution in that regard where the seal is thicker because it's the entire face of the gasket is a seal.
Thanks, Ian. The next question is that you recommend metal cord gaskets at higher pressures. What in your mind would constitute a high pressure here? Is it 200 PSI, 700 PSI, other?
Yeah, and I typically look for a pressure class to break it down in that regard. So like I said, a 600 pound is usually my tipping point. Below a 600 pound pressure class, um, I feel comfortable not using metal core. Above a 600 pound, I definitely do want to use a gasket with a metal core. At that 600 pound, it's kind of a judgment. We can go either way, depending on some other things. But you know, media plays into it. Why I'm not getting an exact pressure, media plays into it. Temperature, that pressure, but that 600 pound pressure rating by ASME is usually what I use as kind of that breaking point of when I'm looking at and giving a recommendation.
Next question is, how can we protect underground piping to above ground piping with conductive fluid using insulating gaskets?
Yeah, so this is what I had talked about a lot. I'm not going to go over the exact same as the internal current transfer, but this is exactly what I was talking about before, that conductive media. So using, first matching the gasket ID, using an ID seal, and if it's very conductive, maybe even protruding that ID seal. And then in another way, a lot of times in these cases, people use monolithic isolation joints. So GPT also manufactures monolithic isolation joints, MIJs. And what this is instead of your bolted flange assembly, so instead of having two flanges with the isolation gasket between, you actually have, we provide a fabricated spool that just gets welded right in and performs all those things. So it isolates, it seals, and you just weld it right into place. And now you have a very long isolating distance because this spool is completely coated, and it isolates right in the middle. And so I can share some information on monolithic isolation joints. And if you have very conductive media and your system can work with these, it's a very good solution to be able to fight this conductive media. So gasket wise, using an ID seal is definitely what I would recommend. And I can share some case studies and some further information with you on that. If your system can use an MIJ, you do have a much longer effective isolating distance with the monolithic isolation joint. Those are two kind of solutions. There's a gasket solution, and then there's a monolithic isolation joint solution as well.
Some great questions coming in, Ian. Just a reminder, everyone, we are past the hour mark. We'll keep going, so feel free to just stay on with us. Ian has been kind enough to stay on with us as well. And I will get to the next question. So that is, can you comment on the importance of surface roughness for selection of isolation gasket types?
Yeah, great question. So we do we do recommend we kind of follow ASME in the recommendation of 125 to 250 AARH surface finish. So it is important. So we want enough of those serrations on the surface to actually bite into the seal itself, to actually get that bite from the flange or from the gasket to the flange, so that we get that seal. We don't want to go above this because once it gets too rough, then you start chewing up that seal material. So above 250 gets too rough, it can damage the seal material. If the peaks are too far away, you might not land a seal on a peak. Too smooth, and you can imagine it's very hard to seal smooth rubber against a smooth flange face. So that 125 to 250 surface roughness is kind of the sweet spot where you get that bite, but it's not too aggressive. With that being said, we've worked a lot with coated flanges. We have solutions for coated flanges, and so with a coated flange, you of course have a smooth flange face. We have done this. We've worked with this quite a bit with our VCS gasket and our Evolution gasket, and had a lot of success. So we do have some solutions for coated flange faces or smoother flange faces, but for best performance, we do recommend that ASME surface or that PCC1 surface finish, so that 125 to 250 micro-inch AARH serrated concentric finish for your flange. That's what we would recommend.
All right, next is, do most contractors install isolation gaskets only at joints transitioning from above grade to below grade and at material type transitions?
Yeah, so at those two places we almost always see them. So above grade to below grade, we see them almost always, and then change of material grade, we see them always as well. So when you have a dissimilar metal connection, you're going to want to break up those dissimilar metals so you don't get that galvanic corrosion. So you don't get that anode, that cathode ratio where your anode is corroding away. Below grade to above grade, we see them, and then all along in CP system design. So there's a lot of examples of where we see them with cathodic protection as well. It could be custody transfer, so where you're protecting your line and you don't want your custody transferring to another line and you don't want to protect their line with your CP system. You put an isolation gasket in there. If we're entering valves or compressors or pumps or anything electrical, you don't want your CP system coming into those specific pieces of material and maybe damaging them if they're using any type of electrical design. Sometimes going into your compressor station or your actual station or your facility or your refinery, whatever it may be, those pipes leading into that, you want to isolate right there so you don't have CP flowing into that system. And then overall, just your CP system, you might have a rectifier that can only protect reasonably a certain distance, and so you break those distances up by using flange isolation kit, so that you're not having a rectifier try to protect this long stretch of pipeline to where you're putting voltage on and it's not actually protecting because it's trying to stretch it too thin. So those are times where we see them quite a bit. They're more, but like you said, CP systems and dissimilar metals are really the big ones that we see frequently. And what you mentioned is almost always see one in those cases, dissimilar metals and below ground to above ground.
Okay, so the next question is, until what temperature can we use these GRE isolated gaskets?
Yeah, great question. So there's two material grades of GRE. The first is G10, and that is good to 302 Fahrenheit or 150 degrees Celsius. And for anything above that, we switch to the G11 material, which is the high temperature GRE material, which goes to 392 Fahrenheit or 200 degrees Celsius. So again, G10 is the standard material and it goes to 302 F or 150 C. G11 is the higher temperature, it goes to 392 F or 200 C. And then we have other gaskets that go above that in temperature, but for GRE specifically, those are the temperatures that you're looking at with G10 or G11.
The next question is, Ian, you recommend a metal core to prevent permeation, but isn't there the possibility of losing isolation with such gaskets?
Yeah, good. That's a great question. So how that design works is that you actually have, so the first one that was invented, you actually have the GRE material laminated onto each side of that metal core. So you actually don't have a metal to metal contact ever. You have that GRE creating your isolation, so your electrical barrier. And then you have a metal core so that the media can't permeate all the way through the gasket itself and out as a leak. And then you have GRE on the other side to create isolation there. So you actually don't have electrical contact. But you are correct. If you just put in a RTJ gasket or a spiral wound gasket or a cam profile gasket with that metal, you're not gonna have isolation from the start. So a lot of the things that we talked about today, if you use a metal gasket, they're all out the window because you don't even have isolation from the start. So it's a great point. But that gasket, the isolation gasket design with the metal core, has isolating material on each side of that metal to prevent anything, to prevent metal to metal contact or conductive to conductive contact.
All right, now the final question for today. Again, there's still some time. We've got a lot of people still here, which is awesome. But for the final question that we have thus far is, what makes GPT's sealing element unique to ensure seals can be made in large diameters?
Yeah, thank you for that question. I appreciate that. So we take a lot of pride. I've mentioned a couple times that volume void ratio, that groove to seal kind of ratio that I've mentioned a few times. So we take a lot of time and pride in machining that groove perfectly around. And what that does is, actually, let me go back to my slideshow and show you. So what you'll see here, so that groove is specially designed so when that seal sits in it, we need that seal to compress once the flanges are torqued. So that seal, that's what's going to make your seal, is that compression. But you need that seal to be able to compress into something. So if this design, if this doesn't have a groove that the seal can compress into, just like this, it might flow over the edge, and over time it's gonna run that seal out, and it's gonna create a leak path. And we see it really time and time again. It's what you see on the left here. So we take a lot of pride in actually machining that groove exactly and putting a sealing element in so that we know exactly how much that seal is going to compress, flow into the groove, and create a tight seal that way. And so it's something we take a lot of pride in. And it, you know, when I first started at GPT, I was like, there can't be much engineering that goes into that, but there is quite a bit, and there is a lot of thought and a lot of precision that goes into it. And that's the biggest advantage of that, of in our large diameter gaskets, being able to seal with that type of seal design, is the biggest reason that we feel confident and have a lot of success. You know, I'll come out to site and we can hydro test, and I'll stand there right there with you. And if it fails, that's you know, the L on my head. And I've done it a few times, and I have just a lot of confidence that these gaskets seal really well once those seals are engaged as a result of that.
Okay, and so with that final question coming through, that brings today's webinar to a close. Again, if we didn't get your question, or if you have any follow-up thoughts or questions, I encourage you to reach out directly to Ian today. His information, again, here is at the bottom in the bottom left corner, pardon me, of the slide. But we'll also share the contact info in our follow-up email. Along with that email, you'll also have a link to the recording directly, so you can reference this in the future. Again, a big thank you to you, the audience, for making the time to view this presentation. And thank you again, Ian, for the wonderful expertise that you've shared today. Have a great day and week, everybody. Bye for now.